Let's continue our discussion of Markov chains with the state vector and state transition matrix. So, as before, consider a discrete time Markov chain written as x0, x1, x2, and so on, and with the following properties to keep things simple. So we'll say it has finite range, so we'll label the nodes as 1 up to k, or any other labels that you like, but we're using 1 through k here just to keep it very simple. So I just write these 1 through k. And we're also assuming the Markov chain is homogeneous, meaning that the probability of jumping from state j to state k in one time step is not a function of time. Okay, so recall that these pjk's are the transition probabilities. So these are the probabilities of jumping from state j to state k in a single time step. So because they're probabilities, they have to be non-negative and they have to sum up to 1. We'll write those properties, but we usually write them in this diagram as follows. So we draw an edge from every node to every other node where there's a positive probability, and we write the value of the transition probability. So in this illustration, we've written an edge from basically every node to every other node, which means that we assume all of those probabilities here are positive. If one of them was 0, we wouldn't draw an arc. Okay, so non-negativity, as I mentioned, means the pjk are not negative, and normalization means that the total probability of all the states you could go to adds up to 1. We also have the n-step transition probabilities, which are the probabilities of going from state j to state k in exactly n steps. That's pjk of n. And we learned in a previous video we can find these using the Chapman-Kolmogorov equations, summing this thing up from I equals 1 to k. So basically it's all the intermediate nodes I that you could go to and just adding up all of those possible paths probabilities. Okay, and pjk1 here is just pjk. All right, it's often more convenient for us to write these transition probabilities as a matrix. Okay, so we could write a big list of probabilities, but it's more compact to write as a matrix and it's easier for operations. So the state transition matrix or transition probability matrix, you'll see that used as well. It's written as this capital P. It's a k by k matrix whose jkth entry is pjk. Okay, so it's a big matrix. The first row has index starting with 1, the second row has index starting with 2, and the last row has index starting with capital K. Okay, so the row index here, it refers to the current state, and the column index refers to the state we're going to, or the next state. And so by normalization, that means that each row has to sum up to 1. It's not necessary that the columns sum up to 1, but they might. The n-step transition matrix is, or n-step transition probability matrix. So this is the same idea, except now we're going to write as capital P of n. So it's a k by k matrix whose jkth entry is the n-step transition probability pjk of n. So we just fill in this matrix with p11 of n all the way up to pkk of n, all right? So we're just writing the same thing as we had before. And the convenient thing about this representation is that the Chapman-Kolmogorov equations for finding the n-step probabilities just turn into matrix multiplication. So if I want to find p of n plus m, just multiply p of n times p of m. So that means that p of n is just p raised to the nth power, and all the other properties above still apply. So normalization, each row sums up to 1, and non-negativity. All right, let's do an example. So what I'm going to do is I'm going to give you the same Markov chain that we saw in the previous video and ask you to figure out the two-step transition probability matrix. So here's that Markov chain. We can see that P11, P12, P21, and P22 are the transition probability matrix. Those values here are going to be a fifth, 4/5, 3/5, and 2/5. And note that the rows sum up to 1, the columns do not in this particular case. So P2 is just P squared. So it's just like taking this matrix and just multiplying it by itself. And in this case, I'm going to work through all those matrix multiplication operations carefully. So I'm going to just write this as a fifth times a fifth plus 4/5 times 3/5 because I took the first row times the first column. Now the first row times the second column. Okay. Now the second row times the first column. And finally, the second row times the second column. All right, so that is how I multiply the matrix by itself. And if I work all of this out, I'll get 13 over 25 and 12 over 25, that sums to 1, and 9 over 25 and 16 over 25. If you remember, in the previous video, we did work out two-step transition probabilities, and we got the same answer. And there we were using the Chapman-Kolmogorov equations without matrix representation. And here we use the matrix representation, but we got the same answer. So all that's happening is in both cases, we're just tracking how probability is flowing from the current state where we are through all possible paths that lead to the next state, which we're interested in. So in this case, every path is possible. So if I start at 1 and I want to know the probability of going to 2 in 2 time steps, I could stay on 1 and then jump to 2, or go to 2 and stay on 2. And I just have to track how all those probabilities flow. All right, the state probability vector, not matrix, but vector at time t is written as this p vector of t. It's a length k column vector whose jth entry is the probability of occupying state j at time t. So pxt of j is just p, the probability of xt being equal to j. And so I write this as a vector for all of the different states. Okay, and so this at time 0 is the initial probability state vector. And what we can do is determine how pt changes in one time step using either the transition probabilities. So I can use this update rule for jumping one time step, right? So I just multiply by the pjk, or the transition probability matrix. And this is an easier way to see what's going on. So to jump from one time step, I multiply by p transpose. And so basically here, we could get away with multiplying with no transposes, but then we would be using row vectors. So I would be transposing the state vectors rather than the state matrix. But I need to have something in that form. So here we're choosing to transpose the transition matrix, okay? We can determine how pt changes in n steps using the n-step transition probabilities as before. So I could work those out using Chapman-Kolmogorov, and then I could multiply them through here to get p xt plus n, or I could use the n-step transition probability matrix. Okay, so what I could do is work out what that matrix is, which is just p to the n, and then take its transpose and multiply it through. Let's do an example. Let's say that I start out in state 1. So I start in state 1 with probability 1, and I want to figure out the state probability vector at time 1 and time 2. So the way I'm going to do that is just multiply by this transpose transition matrix. So I just write that out 1/5, 4/5, 3/5, and 2/5. And so I multiply by 1, 0, and I get 1/5 and 4/5, just the first column. Okay, and now I'm going to update that again. I'm going to multiply again by the same matrix. So I just copy that matrix over 1/5, 4/5, 3/5, and 2/5. And I multiply 1/5 and 4/5 by that to update it. And I get 13 over 25 and 12 over 25. Okay, and notice that all of the entries in the state vector have to add up to 1 because it's the probability of living in any one of the case states. To close out, let's do one more example. So in this case, I'm going to give you the transition probability matrix. So here it is. And then I'm going to ask to work out some quantities, and we'll draw the diagram to help us out. Okay, so here's the transition probability matrix, and here's the initial state vector. So it's 1/3, 2/3, and 0. And so I want to calculate what is the state vector at time 2. Okay, so here's the diagram. So I have an arc from 1 to 2. an arc from 2 to 1, an arc from 2 to 2, an arc from 2 to 3, and an arc from 3 to 1, okay? So state vector at time 1 is just P transpose times P0. So I transpose this matrix, I multiply it by P0, which is just a third, 2/3, and 0. And then if I work that out, I'm going to get a 1/6, 2/3, and a 1/6, okay? For P2, I do the same thing. I hit it by P transpose, and I'm going to write out P transpose again. I'm going to write now P1, which is going to be a 1/6, 2/3, and a 1/6. And I'm going to get 1/3, 1/2, and 1/6. Okay, now for something a little more tricky, I want to calculate the probability that x0 is 2, given that x2 is equal to 3. Now, this is a reverse time direction. So usually what we've been doing is starting out at a given time and going forward. And now I'm asking you to go backward in time. So I'm saying if you observe at time 2, you're sitting in state 3, what was the probability that 2 steps ago you were sitting in state 2? And because we're flipping the conditioning here from what we usually do, we should use Bayes' rule. So I'm going to flip the conditioning to say x2 equals 3 given x0 equals 2 times probability x0 equals 2 divided by the probability that x2 equals 3. Okay, and this is just Bayes' rule from way long ago. We're just reapplying it here. It turns out I know some of these terms already. Px0 equals 2 is from the from the state vector, and this is also from the state vector. So what I need is P of x2 equals 3 given x0 equals 2. So let's see what can happen. So I can start at 2 and go to 1, and then I come back to 2. So that doesn't go from 2 to 3. So that doesn't work. I can start at 2 and then stay on 2 and then go to 3. So that works. So I'm going to write down those probabilities, 1/2 and 1/4, because I have 1/2 probability to stay on 2 and then 1/2 probability to go to 3. So in 2 steps, I can go from 2 to 3 by staying on 2 and then going to 3. Can I go to 3 first? Well, if I go to 3, then I come back to 1. So that doesn't work. So basically, I saw that of the 3 choices, go to 1, stay on 2, and go to 3, the only move that gets me to 3 in the next time step is to stay on 2. If I go to 1, then in the next time step, I'm back on 2, not 3. If I stay on 2, then I could go to 3 in the next time step. So I included that probability, 1/2 times 1/4. And if I go to 3, then I'll be thrown to 1 in the next time step. So that doesn't work. So I only have, in 2 steps, the only way to do it is to stay on 2 and then go to 3. And I wrote down the product of those probabilities. So I get an 1/8. So then this is just an 1/8 times 2/3 divided by 1/6, which is 1/2. And that's it.